One of the features IPv4 protocol deals with is datagrams fragmentation. Why does it happen? First, we know that the largest possible datagram we can transfer through the link is hardware limited. This limit is also called Maximum Transfer Unit Size, or MTU. Different links, and there are several types of links, have different sized MTU. Usually, if we're in a classroom and we're in Ethernet links, it can be 1500 bytes. But in the general internet and in the world, it can sometimes even be 256 bytes. And in links to satellites, it can be 128 bytes or less. So large datagrams of IP, once we go toward transmission, must be divided into fragments, and at the fragment's reception point, there should be a process called reassembly. The bits that exist in the IP header and other fields help us with that. For example, we see here an outgoing datagram. It reaches a certain point, from which the MTU is significantly smaller. The datagram is divided into 3 pieces or fragments that are transmitted. Once they reach the endpoint, we can see the reassembly process. Why was the large datagram divided into 3? We saw, when we reached the router, that to its left, the MTU is larger, and to its right, the MTU is smaller. Therefore, the large datagram cannot enter the MTU size. Let's assume it was 1500 on the left, and on the right, we had a size of 600. And so the fragment was divided into 3, and later it was reassembled. Let's see an example. We have a 4000 bytes datagram. The MTU's size is 1500 bytes. Therefore, we first need to divide it into 3 fragments. What do? We first connect all of those fragments with an ID. We write the ID in the ID field in the header IP, and it is usually a number that is set at this point. We try to have a rising and unique ID. It is given once a datagram has been transmitted, in case fragmentation is required. And once we do fragmentation, we copy the ID, we mark the More Fragments flag on the first datagram 1, on the second datagram 2, and on the last datagram as 0. This helps us with the assembly and the offset, which is measured in octets, not bytes, but octets. For the first one, it is 0. For the second we see 185, and for the third, 370. The first datagram is flag equals 1, with offset equals 0. The last datagram is flag equals 0, with an offset larger than 0. And in the middle, it's flag equals 1, with an offset larger than 0. This is how we tell if it's the first, middle, or last fragment. Usually, when we get a flag that is 0, we know it's the last datagram, on the condition that there is something in the offset. Then you know what the last datagram for reassembly is, and you also know that you received the last datagram. And if you received all the datagrams in the middle, you're not supposed to get any additional datagrams. You don't need to wait for them. You can start the reassembly. If a fragment doesn't arrive, it's not very nice. Usually, whoever is doing the assembly gets some timer that is according to RFC something like 60 seconds, and then it waits for fragments. But if a fragment still doesn't arrive, then it was missed or lost in the networks, and we are forced to crash all the datagrams. Therefore, fragmentation is not a desirable thing. It's something we're forced to do.